Mechanical comprehension, pulleys. Pulley systems are simple machines designed to make lifting a load easier. So a pulley system can help you redirect the force, like in this instance. Without the pulley, you'd have to just pick it up directly from the ground. But with this pulley system, you can change the direction of the force you apply. A pulley system can also be used to reduce the amount of force you need to apply in order to lift the load, or in this instance, reduce the force and redirect the force. But there's a trade-off. The force required to lift the load is less, but the distance you have to pull the rope increases. For example, in this simple redirection pulley, to lift the load 1 meter, you have to pull down 1 meter. In this example of a pulley system that reduces the force and redirects the force, in order to lift the load 1 meter, you have to pull the rope 2 meters, but you're also reducing the force by half. In a pulley system, the tension is going to be the same through a rope. So the tension on this side will be the same as the tension on this side. And in this example, the tension here will be the same as the tension here, which will also be the same as the tension here. A pulley system is made up of these pieces. It has a rope or a cable running through the wheels. You can have a fixed wheel like this one here, it stays in place, or a movable wheel like this one here, which moves as the load is raised or lowered. And the applied force is from you or the person pulling the rope, which then lifts the load. There are different types of pulley systems. Most commonly, we're going to encounter a simple pulley system, and you can identify a simple pulley system by how many ropes are in the system. So here, there's just one rope that starts here, goes around this movable pulley, around the fixed pulley, and then to the person applying the force. This is what's known as a compound system. The fundamentals are the same. However, a compound system is really just multiple simple pulley systems joined together. So in this case, there's two complete simple pulley systems joined together. And you can tell there's multiple systems because there's multiple ropes. This rope starts here, finishes here. That's one rope. And the second rope starts here, goes around the movable pulley and finishes here. Let's look at how we determine how much force is required to lift the load. In this first example, it's a simple pulley system and it's just redirecting the 100 Newton load. We can figure out how much force is required to lift the load by determining how many instances of rope are supporting the load. And we can visualize this by drawing a box or a free diagram around the movable portion of the system. So here you can see that there's just one rope supporting this whole system. And if the load is 100 newtons pulling down, the tension in the rope must be supporting 100 newtons. As you follow the rope up, it moves around this fixed wheel and the tension will remain the same on both sides because it's just one rope. And so you'll require 100 newtons in order to lift this load. Let's look at the next example. So here we know that the load is pulling 100 newtons. So this piece here has 100 newtons of tension in it. If we draw a box around the moving portion of this pulley system, you can see that it's supported by two instances of rope. It's the same piece of rope, but there's two instances of it. What that means is the 100 newtons of force pulling down in this box is supported by two instances of rope, and that force is divided amongst those two instances. So each piece is supporting 50 newtons of force. If we follow this side of the rope up around, we know that the tension will remain the same on either side of this pulley, and therefore the force required to lift the load is 50 newtons. What about in this example? Same thing, 100 newtons pulling down. If we draw the free body box around this moving portion of the pulley system, we can see it intersects at 3 different points. So there's 3 instances of this rope supporting the 100 newtons of force. So you just simply have to divide the 100 newtons of force by 3, gives us approximately 33 newtons of force on each portion of the rope. Now this is one continuous rope, so we know that the tension will remain the same. And if there's 33 newtons on this side, there must be 33 newtons on this side, and therefore the applied force to lift the load is 33 newtons. Now what about in this system here? So we know that there's 100 newtons pulling down, and if we draw a box around the movable portion of the system, you can see it intersects at 4 different points, which means the 100 newtons is supported by 4 instances of rope. And if you divide 100 by 4, it gives you 25 newtons on each piece of rope. And since this is all one continuous rope, the tension will remain the same all the way over to the applied force side. So we have 25 newtons of force in order to lift the load. Here's one more example in which we have two loads, 100 newtons each, totaling 200 newtons of load. Now this is one continuous rope, so it's one system. If we draw a box around the entire movable portion of the system, we can see it intersects at 4 different times. If the total newtons pulling down is 200, we divide that by the 4 instances, we can see that there's 50 newtons of force at each point. Now because it's one continuous rope, we know that 50 newtons of tension will remain constant, and the input force required to lift these two loads is 50 newtons. Now what about this system? We talked before about a compound pulley system being multiple simple pulley systems joined together. And we can tell this is the case because there's more than one rope. So we know there's 100 newtons of force pulling on this portion of the system. Because there's two separate pulley systems here, we have to draw a free body box around this portion of the system and around this portion of the system. So for each separate piece of rope, there's a free body box around the movable portion of the system. It's still very simple to figure out. On this free body portion, we have the rope intersecting twice, and it's supporting 100 newtons of force. If we divide 100 by 2, we end up with 50 newtons on either side. Now, when it comes to this portion of the system, we know that the downwards force is only 50 newtons, and it's supported by 2 instances of rope. So if we divide 50 by 2, we get 25 newtons on either side, and therefore the input force required to lift this load is 25 newtons. What about this system? This is the same concept as the previous example, except there's 3 separate systems. We know this because there's one portion of rope here, one portion of rope here, and one portion of rope here. That's 3. So 3 different pulley systems in order to lift one load. If we draw our free body box around each movable portion of each system, we can quickly determine the tension forces in each instance of rope. So here we've got 100 newtons pulling down on this portion of the system, and it's supported by 2 instances of rope. So if we divide 100 by 2, we end up with 50 newtons in this portion, 50 newtons in this portion. So that means this free body section of the system is supporting 50 newtons of force. And it's supported once again twice. So if we divide 50 by 2, we have 25 newtons in each side of this system. Now this system here is pulling down with 25 newtons of force, and it's supported by 2 instances of the same rope. So if we divide 25 by 2, we end up with 12.5 newtons on either side. And as we know, the tension remains the same in one piece of rope, and therefore the input force required to lift the 100 newtons is 12.5 newtons. Let's look at this example here. We have this load with 100 newtons pulling down, and we have this man here trying to lift it. So there's one movable pulley and one pulley that just redirects the load. So if we draw our free body box around the movable portion of the system, we can see it intersects the rope twice. So there's 2 instances of rope supporting the 100 newtons. And there's just one rope, so it's just a simple system. So each instance of the rope is supporting 50 newtons, which is half. We figured that out by dividing 100 newtons by 2, which means that this person has to pull at least 50 newtons in order to support the load. What happens if he can only pull 30 newtons? It's not enough to support the load, and the load will move down.